runs towards it. The Earth there's still this huge gravitational pull, and the Earth is still orbiting it. Just like the black hole at the center of the Milky Way galaxy. I mean, we haven't gotten sucked in yet.
Not yet.
I guess those people with solar panels are fucked, huh?
Yeah, the solar panels that would be of limited use.
And we have to make a nocturnal panel that draw energy off darkness.
I don't think the nocturnal.
It's just a name.
I suddenly had an image of the moon, but the moon we wouldn't see the moon at all without the sun.
We're still waiting on your thesis statement, by the way.
Oh, that's right.
Disappointed. We have due dates, you do too.
Always we can leave people wanting more. All right. I at least wanted to hit on that. Momentum is the next bit, so let's talk a little bit about some of the chapter 8 stuff. There's a video for the derivation, so we'll just jump straight to the formula for momentum. Recognize momentum is a vector. Unlike work and energy, those are scalars. Momentum is a vector. If I did the change in momentum over the change in time, well, that would be the change in mass times velocity over the change in time. If the mass doesn't change, so I've got some object which doesn't disintegrate or break or anything like that, I can factor mass out. I get mass times the change in velocity over the change in time. What's the change in velocity over change in time?
Acceleration.
Yeah. And what is mass times acceleration?
Force.
Total force.
Well,
So we have this other relationship here that force is equal to the change in momentum over the change in time. This idea that force is the change in momentum over the change in time is a slightly more generalized equation to Newton's second law. What would this take into account that Newton's second law does not?
Time.
There's time built into acceleration.
How fast it's going originally.
Newton's second law does not take that into account. This doesn't either. If I make the claim that force is equal to the change in momentum over change in time, so that's the change in what are two different ways that the momentum can change?
Mass changes and velocity changes.
Yeah. Velocity changes, that's Newton's second law. But if the mass changes, Newton's second law doesn't quite deal with that particularly well. And so this actually would end up being mass times the change in velocity over the change in time, plus the velocity times the change in mass over the change in time. So just wanted, again, one of the reasons why I wanted you to have the formula for kinetic energy memorized is that that is going to hold true. But Newton's second law, there is a more generalized form. What's an example of something that changes its mass as it moves?
A car burning fuel.
That'd be one of them. Yep.
A snowball rolling down a snowy hill.
Oh, gaining mass?
Yeah.
Okay. And then there's the classic in physics textbooks, the rocket problems, where it's also burning fuel.
wouldn't people also change their mass? as they
Wouldn't what?
continue- Wouldn't people also change their mass as they continue on?
Oh, as in just the metabolism?
I guess.
Yes, typically you don't use this for the small changes in mass, but you would be correct as well. Now, there are 3 conservation laws of physics. Conservation of energy, conservation of momentum, and conservation of angular momentum, which we haven't officially gotten to yet. Because we can approach any problem from the point of view of, well, actually, Newton's laws, or from the point of view of energy, or from momentum, or angular momentum. And the one that you pick is the one that makes the most sense. Or actually, the one you should pick is the one that is the easiest math-wise. So conservation of energy, typically, if you got something changing elevations or changing spring length, conservation of energy, it's a good one. Conservation of momentum works really well if there's a crash or a collision. So if ever you see a problem in which a collision occurs, you should immediately think conservation of momentum. All right, hopefully review here. If it is a perfectly inelastic collision, what happens to the 2 objects when they hit?
They bounce off each other.
Or the opposite of that?
Is all energy lost?
Say it again?
Is all energy lost?
Not all energy. The maximum amount of kinetic energy will be lost.
It stops.
No. They're not necessarily stopping. I mean, you can set it up so that they do stop, but they're not necessarily going to stop. All right, so the 3 types of collisions in Fox speak. We have the perfectly inelastic collision, we have the imperfect collision, and then there's the perfectly elastic collision. And then Flubber-esque. And there's one of the videos that go into explaining why my language is probably potentially a little bit different than the textbooks. Perfectly inelastic collision, they stick together. Perfectly elastic collision, the change in kinetic energy is 0. In perfect collision, change in kinetic energy is less than 0, but don't stick together. And then Flubber-esque, 2 objects collide and they gain kinetic energy. If you're not familiar with the movie Flubber or The Absent-Minded Professor, you might want to watch it. Personally, I recommend Absent-Minded Professor, the Fred McMurray version. So that's a matter of taste, I assume. I will tell you, on the last test, there will be a problem where I have 2 objects that collide into each other in a perfectly inelastic collision and a perfectly elastic collision. There is a formula in the textbook for a perfectly elastic collision, which I am not going to give you. So please know how to solve them. I've got several videos talking about different techniques for solving it. Let's take the simplest of these cases, the perfectly inelastic collision. 5 kilogram mass going to the right at 3 meters per second. I have a 4 kilogram mass going to the left at 2 meters per second. They will collide in a perfectly inelastic collision, which I will often abbreviate as PIC. What is the final velocity? The nice thing about conservation of momentum is, unlike with Newton's laws, we would have to look at how is the force changing during the entire time of contact. But with conservation of momentum, I don't care what happens in the middle. What I care about is at the beginning and at the end. So let's start out with, what is the momentum of this object? I need more.
I don't know the unit.
How'd you get 15?
30 times 5
Okay, what are the units that you multiplied together?
meters per second and kilogram,
Therefore, the units would be,
kilogram meters per second.
yes.
Is there a shorthand for that?
There is not. Do you want one?
No, that's fine.
I do allow you to make up your own unit if you wish. Please do not use a unit that we are currently using. So if your name is Ned and you want to celebrate yourself and use a capital N, no, that's already being used for Newtons. One thing that I will often use is René Descartes was doing some early work with momentum, and so I create my own unit of the Descartes, which I define, that's the 3 equal sign. It's equal by definition to a kilogram meter per second. Some students latch onto this, some students don't. Right? Kilogram meters per second is also fine. Kilogram meter per second is also a Newton second, so some students prefer that. As with any compound unit like this, if you're kilogram meters, please put a dot in between. Although not particularly crucial, well, as crucial there, but if I have a Newton meter, that is the same as a meter Newton, which is different than a millinewton. Those are not the same. All right. Now, Cooper established something that he didn't state. What assumption did Cooper make?
Is it that they're already in motion?
No, that I established that.
The mass is constant.
But I have 2 voices at once. Sorry. Mason?
The mass is constant.
We are, yeah, that's not Cooper's doing. There's another voice.
That's what it said.
Ah. All right, perhaps it'll become clear. What's the momentum of this one?
8 kilogram meter per second.
And I will say that one of you is wrong. I would say Ethan's wrong because Cooper went first.
Did I assume that right is positive?
That's exactly what Cooper did. As soon as he said 15 instead of negative 15, that establishes our convention here. We are dealing with vectors. Direction matters. What is the momentum of this one then? Yes. There is a difference between them coming towards each other and one pursuing the other one. So what is my total momentum? So P initial, 7. Descartes, since I have it defined over there. What's my final momentum after they collide? Oh, in unison would be really nice right now.
7.
That sounded like a single voice. That's how unison it was. Excellent. Yes. The whole idea of conservation of momentum is whatever I start with, I end with. So P final. There's a test a number of years ago where I did a problem like this. So part A is what's the momentum of that, what's the momentum of that, what's B, what's the total initial momentum. What's the total final momentum? Shocked at the number of people who missed it. Because it's a perfectly inelastic collision, what do the two objects do when they hit?
They stick together.
So after the collision, that final momentum is going to be equal to the mass, which is now 9 kilograms times my final velocity. They have become 1. So the final velocity is
7 ninths.
0.7 per meter.
Meters per second.
I guess that makes a little slight division there. And this next bit might make some people feel a little sad.
I'm sad all the time.
If I have 7 is equal to, see if I can do this more neatly. 7 equals 9v. V is equal to 7 ninths. Some of you on the test yesterday thought it should be equal to 9 sevenths. Now, if you're not sure which problem I'm talking about the 5 kilogram mass that had a 5 newton force, 145 kilogram mass. It was a small acceleration. All right, all that's well and good. Let's do one more where the numbers work out more nicely, because I know what I'm doing after this. All right, that'll work. All right, you should be able to do this one. I got make sure I do the right numbers here. 46110. 4 kilograms. Going to the right at 6 meters per second. And then I have a 10 kilogram mass. Going to the left at 1 meter per second. Let's see, 461. All right. In a perfectly inelastic collision, what's my final velocity?
0 meters per second.
Pardon?
0 meters per second.
No, not 0.
1 meter per second.
Yes. How'd you get it?
I did 4 times 6 equals 24, and I assumed the right was positive. And then I did 1 times 10 is negative 10, since it's in the left direction. And then I got the final momentum was 14 kilogram meter per second. And then I did, that is equal to 14, because they're now stuck together in one mass, times the velocity.
All right. Now I'm going to take these two objects and put them in a perfectly elastic collision. But first, let's take a small little break, stretch legs. We'll come back and we'll handle the perfectly elastic collision where kinetic energy is conserved. Perfectly elastic collision. Kinetic energy is conserved. Well, we know that the total momentum is conserved also. It's a collision, and there's nothing else involved here. So I know that my initial momentum is 24 plus -10 or 14. Still defined, still good with that. If I erase this, and again, this is in the video, but reiterating, if I erase this, then that's suddenly wrong. Because D is not a legitimate unit for this, so I have to have it defined in order for me to use it. M1 V1 final plus, four final plus 10 V. All right,
What is that under the first V, 4V?
4 right here,
Yeah.
4F. I try to make the subscripts have some meaning to what I'm starting with. That's a 4 kilogram mass, so I did 4. And the 10 kilogram mass, I didn't feel like writing 10, so I just did a 1. Just as long as the subscripts are different. I'm gonna take it one step further, just because the more I write, the more chances I have of making a careless error. So I'm just gonna let the letter C represent 4 the final, and let D equal the final velocity of 1. In other words, the 10 kilogram mass. So that first equation just becomes 14 is equal to 4C plus 10D. What you've missed is just, it's the same problem, perfectly elastic collisions, so they're not sticking together, and this is conservation of momentum. You start out with 14 units beforehand, we better have 14 at the end. Okay, questions up to here?
So we have two D's in the same equation, or the same problem.
Sorry, say it again?
One meaning the unit of kilogram meters per second, and one meaning D10 final.
Oh, yes, you are right, that is bad.